Picture a material so adaptable that it preserves your food, insulates your walls, shields satellites from radiation, and finds its place in works of art. A substance so delicate you can tear it bare-handed, yet resilient enough to endure extreme temperatures and guard against contamination. This is aluminum foil, something we reach for every day without a second thought. But what really is aluminum foil? How is this astonishingly thin metal sheet actually made? And where does its story begin? The answer might surprise you. Its creation demands some of the most advanced industrial processes ever engineered. It's far more than simply flattening metal. Let's explore the science, history, and reality behind this everyday marvel right here on History of Ordinary Wonders. At its heart, aluminum foil is an exceptionally thin sheet of metallic aluminum, generally ranging from 0.2 millimeters down to as little as 0.006 millimeters in thickness. Despite its fragile appearance, this ultra-thin metal carries remarkable properties that make it indispensable across a vast range of uses. When exposed to air, aluminum naturally develops a protective oxide layer, granting it strong resistance to corrosion. It forms an outstanding barrier against moisture, oxygen, light, and bacteria, qualities that explain its dominance in food packaging. Aluminum conducts heat with impressive efficiency while staying lightweight and entirely non-toxic. These combined traits produce a material that is simultaneously protective, practical, and safe for direct food contact. Perhaps surprisingly, aluminum foil doesn't begin its life as metal. It originates deep within the earth as bauxite ore, a reddish-brown rock rich in aluminum oxide and the primary global source of all aluminum. Significant deposits are found across Australia, Guinea, Brazil, and Jamaica. Extraction happens through open-pit mining, after which the raw material is washed and crushed in preparation for a complex refining journey. Converting bauxite into metallic aluminum demands two separate industrial stages. First, the Bayer process draws pure aluminum oxide from the bauxite. The ore is crushed and dissolved in hot sodium hydroxide solution under high pressure, allowing aluminum compounds to separate while impurities are filtered away. After cooling and crystallization, a fine white powder called alumina emerges, the essential precursor to metallic aluminum. The second stage, the Hall-Héroult process, transforms alumina into metallic aluminum through electrolysis. This energy-intensive operation takes place inside massive cells filled with molten cryolite at around 960 degrees Celsius. Powerful electric currents sever the chemical bonds in aluminum oxide, releasing pure molten aluminum. The process is extraordinarily demanding, consuming roughly 15 kilowatt-hours of electricity to yield just 1 kilogram of aluminum. With molten aluminum secured, the next phase involves alloying and casting. For food-grade foil, minute amounts of iron and silicon are introduced to boost strength. The aluminum alloy is then cast into large rectangular ingots, typically weighing several tons, which cool gradually under controlled conditions to avoid internal stresses that could compromise the finished product. The journey from heavy ingot to wafer-thin foil begins with hot rolling. The ingots are reheated to approximately 500 degrees Celsius to increase their malleability, then fed repeatedly through powerful rolling mills that apply immense pressure. Each pass progressively reduces the thickness, turning a slab nearly half a meter thick into sheets of roughly 5 millimeters. From there, cold rolling takes over, working at room temperature to drive the metal to extreme thinness while simultaneously strengthening it. Multiple precision passes bring the sheets thinner and thinner, with periodic annealing treatments applied between stages to relieve accumulated internal stress. Achieving thicknesses below 0.025 millimeters introduces a unique challenge, one solved through pack rolling. Two aluminum sheets are stacked and rolled together simultaneously. The surface in contact with the steel roller acquires a bright, shiny finish, while the surface pressed against the adjacent sheet develops a matte texture. This is precisely why household aluminum foil always has one gleaming side and one dull side. Once target thickness is reached, the foil undergoes final processing. Food-grade foil is thoroughly cleaned to eliminate residual rolling oils, and many foils receive specialized coatings or laminates. Heat-sealable coatings allow the foil to bond under heat, a critical feature in sealed packaging found in everything from juice cartons to pharmaceutical blister packs. The finished foil is wound onto massive master rolls holding thousands of meters of material, which are subsequently slit into narrower widths for specific applications. Household rolls are trimmed to standard dimensions and wound onto cardboard tubes. Throughout every stage of this process, continuous quality control systems monitor thickness uniformity, surface integrity, and dimensional precision. The environmental footprint of aluminum foil production has drawn growing scrutiny. Bauxite mining disturbs natural ecosystems, and the electrolysis process is a significant consumer of electrical energy. Yet aluminum's exceptional recyclability offers a meaningful counterbalance. Recycling aluminum requires only 5% of the energy demanded by primary production from bauxite, and unlike many materials, aluminum can be recycled indefinitely with no loss in quality. Aluminum foil's usefulness stretches well beyond the kitchen. In construction, it functions as radiant barrier insulation. The aerospace sector relies on it for spacecraft thermal protection. Electronics manufacturers use it as capacitor electrodes and electromagnetic shielding. The pharmaceutical industry counts on it for blister pack medication. This extraordinary breadth of application speaks to aluminum foil's rare combination of physical properties. Appreciating aluminum foil means recognizing the sophisticated chain of industrial processes that transforms a mineral dug from the earth into a versatile metal sheet measuring a fraction of a millimeter. From bauxite mining through chemical refining, electrolytic reduction, and precision rolling, every step builds toward a material of unique and enduring value. That shiny sheet you casually pull from the roll is the culmination of over a century of engineering ingenuity and scientific advancement. It continues to serve countless essential roles in modern life. And the next time you reach for it, you'll know you're holding the result of an extraordinary journey from rocky ore to one of civilization's most quietly indispensable materials. Thank you for watching. If you have suggestions for our next video, feel free to share them in the comments below. We'd love to give you proper credit for your ideas. Thank you for joining us on this journey through history of ordinary wonders. Don't forget to like, subscribe, and stay tuned for more stories uncovered through the smallest details.